All right, so yeah, today we're going to close out our discussion of beams. So continuing and finishing, hopefully, part two of our discussion of bending of beams and plates at the same time, because, it was fun and because they're not so different after all, beams and plates. Why can't they just get along? So we'll finish both of those subjects, and then we'll reserve time at the end to move on to torsion, really the primary subject of today's lecture. And just to give you a brief recap of all of the different equations and relationships between these different quantities of interest in the case of beam bending problems really can be boiled down into, if you like, really just one unknown field or one unknown kind of expression for the transverse displacement of a beam. And instead of representing it as displacement in the y direction or displacement in the z direction, I'm just kind of being fast and loose here and calling transverse deflection, transverse displacement as W. It could be either one of those two different components of displacement. In general, it might displace in either one of those two directions, but if you treat everything as being kind of in a plane two-dimensional setting, we can just call either one of those W and then proceed as normal. And then we found a bunch of different relationships. We related this transverse deflection field through some kind of differential relationship to the resulting kind of rotation angle of a given cross-section by assuming relatively small shear deformations. And then we've found some relationship between, that kind of transverse deflection field and the resulting curvature of some kind of line segment that might undergo some bending, local to some region in the beam. From that, we found how did the axial strain vary through the section linearly as a function of this kind of bending curvature, kappa. We applied our normal constitutive law to relate that axial strain to axial stress. We found what was the resultant moment acting on the cross-section given this kind of assumed possibly linearly varying, but not necessarily linearly varying stress distribution through the depth of the cross-section. And then we found through application of equilibrium, both sum of moments and sum of shear forces acting on a small subsection of a beam of finite length delta x, we posed moment equilibrium and shear force equilibrium on that subsection and considered what happens as we shrink this kind of length of this section of the beam down to almost zero length. And we obtained these differential relationships governing how the variation in moment is related directly to the resulting internal shear force. And then the variation in shear force is directly related to whatever transverse loading Q you might apply to the beam. Now, you could represent everything in terms of this big, set of, relationships and try to relate each one of these things to one another, or you could kind of push them all together into one big equation to rule them all, as I like to say, that basically states what happens to a beam purely in terms of that single unknown field, the transverse deflection field. So if you know that, then through all of these relationships, you can figure out everything else. And really, the statement of equilibrium, this is effectively the equilibrium equation. We've just substituted everything else into it. This equation of equilibrium, again, is expressed purely in terms of this displacement-like quantity, the transverse deflection field. And we can solve it, this fourth order differential equation, to figure out what that transverse deflection field is, given whatever applied loads that we might have put onto this beam, that kind of possibly varying distributed load Q, and then we might have some other things like, the second moment of area I showing up here also, as well as the material property, the Young's modulus E. And the situation is actually quite similar, at least in concept, when we look at plates. Here, though, it becomes a little bit more challenging because we have, indeed, transverse deflection is the single unknown field of interest that we're trying to solve for if we're looking at a plate subjected to some kind of transverse loading Q that acts in maybe like the Z direction. Let's call that the transverse direction. So we want to know what is the resulting transverse deflection under some applied transverse loading. We can relate all these different quantities in a similar fashion to one another. We can push them all into one big equation, and we can solve for what is this resulting transverse deflection. governed by, shear force, equilibrium, moment equilibrium, all these different relationships kind of consolidated into one single expression. And it turns out that the resulting expression that you get, it's basically a single governing differential equation of fourth order. And it turns out that this particular governing differential equation is actually the biharmonic equation, which, if you remember way back when we were talking about the Airy stress function and the requirements that the Airy stress function had to satisfy in order to yield solutions that basically were compatible solutions to some kind of two-dimensional problem of plane stress or plane strain, the actual equation it had to satisfy was, in fact, the biharmonic equation. So we've actually come back full circle. It shows up in a different context now, because it's no longer a statement of compatibility, and we're solving a totally different problem, and the parameters that we plug into it are totally different. But at the end of the day, it's worth noting that differential equations are differential equations. You can solve them all in similar approaches as you would for the Airy stress function by posing what is this Airy stress function that generates these stress components that automatically satisfy equilibrium and also satisfy compatibility, i.e. the biharmonic equation. But in that case, the Airy stress function itself didn't really have a good physical interpretation. It was just this fictitious thing we came up with. Now, however, in the case of plate bending, this field, this kind of scalar field that we're looking for, actually does have a definite physical interpretation, and it is, in fact, the transverse deflection field of the plate. So varying potentially as a function of position, in plane position within the plate. So we're looking for this kind of two-dimensional solution, and you would kind of visualize it as basically a three-dimensional plot, varying with in-plane coordinates x and y, and the actual height of this function uz would be illustrative of the actual deflection that this bending plate would undergo. So kind of interesting. Now, in terms of actually solving these types of problems, we'll isolate attention just to beams because this is probably a little bit more tractable to do. But really, the idea is we want to solve that differential equation pushed all together that includes all these different relationships depending on one another to find out what is the transverse deflection field for this beam, let's say, that might be subject to a variety of boundary conditions. So we're still solving boundary value problems, and we can still view everything through the lens of the framework that we've constructed in the theory of elasticity in posing these well-posed boundary value problems, and they are subject to similar requirements as we had in the case of these more complicated situations where we're looking at maybe a two-dimensional plate, and we had to specify along the entire boundary all the different, specific specifications of either displacement or traction, each component along the boundary. And it was a lot of work. There were a lot of different things that we had to specify everywhere in a very granular sense. Now, in the case of solving these more simplified beam bending types of problems, the notion of boundary really has a different interpretation. And, technically speaking, the whole boundary does include these lateral surfaces, including that surface on which we're applying this transverse load Q. But now, really, boundary, I think, is probably more well-defined as really just the ends of this beam. So really, the left-hand end and the right-hand end are what I'll call the appropriate boundaries of this beam. Certainly, we have some distributed load, but for the purpose of doing the analysis, it appears more like a body force than it does an actual boundary traction. So we can treat it more like a body force and treat only these ends as the boundaries of this beam. But to be consistent in actually fully specifying the boundary conditions on every exterior end of this beam, we have to specify one of two things at each end of this beam. Either we have to specify some kind of displacement-like constraint, or we have to specify some kind of stress-like constraint, and those two things are mutually exclusive. So, for example, in terms of the different types of displacement-like constraints, we can either constrain transverse displacement, or we can constrain relative rotation of the section at one of the ends. Alternatively, we could prescribe what is the end shear traction, or what is an end shear load that we might apply to the end of one of these beams, or what is kind of like the end applied moment that we might apply to some end. But if we specify transverse displacement, we cannot also specify this kind of end shear load. Or if we specify rotation, we cannot also specify what is kind of like the moment that would show up as a reaction force to keep the whole thing in equilibrium. So you have to specify one of these four different boundary conditions at every kind of boundary or at each end of this beam. And you also have to specify it in such a way that the beam isn't going to, rigidly deform in an unconstrained way. So we have to prevent rigid motion. It can't be such that we just kind of like don't constrain it at all, or maybe we don't constrain rotation and instead we apply some kind of moment, then it would just rotate. So we have to at least simply support it and prevent it from rigidly translating and rotating. But nonetheless, setting up all these boundary conditions really has the same interpretation as we did in these two-dimensional elasticity problems. So we have to be specific about what the boundary conditions are on both ends of the beam, and we can solve these boundary value problems by basically taking our equilibrium equations and then kind of working backwards almost. So the basic procedure is one that maybe you've seen before. Maybe you've gone through this procedure when you were in your strength and materials coursework, or maybe in a structural analysis class. But just to refresh your memory of maybe that's been a while, or maybe this is something that wasn't an approach that you used very frequently. The approach that I'll suggest is doing successive integration, given whatever this applied load is, expressed as a function, basically, a variable function of position along the length of this beam. I can just take this function and integrate it to basically revert this relationship between transverse load Q and the shear force V, which might vary throughout the length of the beam. So the shear force is basically the integral of this transverse load function. And if I want to be consistent about how I'm actually representing this integral, it's an indefinite integral, so I should probably add a constant of integration. I can do the same thing again by basically saying, really, shear force is the derivative of moment with respect to x, so I can take its integral with respect to x and come up with an expression for how moment varies by integrating the shear force, add another constant of integration. And at this point, you probably get the idea that it's really just a matter of kind of reverting each of these different differential relationships that we've developed, as well as inverting our moment curvature relationship when we go between moment and section rotation, or you could think of this also as the slope of the deflected shape of this kind of beam. But basically, it just amounts to doing integration 4 times. So in this particular example, we start off with this transverse, loading function Q. Let's say it's just a constant Q bar. So integrating this function really amounts to just integrating a constant, which means that the resulting integral of a constant gives me what? Linear? Yes. So if I have a constant function, the integral of this constant function with respect to x will give me a linear function. Conversely, you can think of it as a linear function. Its derivative with constant slope gives me basically constant, derivative. So I do indeed have this kind of linear function. And also, it's important to note that at least for this boundary value problem that I've constructed, I've also specified what is the end shear force at one of the ends of the beam. So actually at the right-hand end of the beam, I've specified that the shear force there has to be equal to 0. I'm technically not applying any kind of end load there, but knowing that actually is crucial information. It allows me to actually figure out exactly how this linear function should vary, such that I can actually set what this constant of integration A is. So knowing that the shear force has to be equal to 0 at the right end allows me to actually figure out that constant, and I can just kind of plug it into the expression and continue in the same fashion. Integrate the shear force with respect to x. A linear varying function now gives me its integral Parabola, yes, yes. A parabolic function. And here too, I have another boundary condition. This time it's a constraint on the end moment. I know the end moment has to be 0, and I can use that boundary condition with the resulting expression that I get from taking this integral in order to figure out exactly what that kind of end value is. And I can set some more constants of integration that way. I can do it again. This time I have to actually go through my moment curvature relationship though. Given moment, I can just divide through by EI, the section stiffness, to get the curvature. So kind of going the opposite direction. This would be obviously a little bit more complicated if you had biaxial bending going on. If, let's say, EI, where I was really a tensor, if you recall, in that case, if I had maybe 2 bending moments, bending about X and bending about Y, or whatever the 2 transverse directions are, to invert this relationship, I should really be inverting this 2x2 matrix or this tensor in order to figure out what are the resulting components of curvature with respect to the different axes. So there might be some interaction. Some moments about X and Y might generate, some interacting bending curvature about opposing axes. But if I do everything with respect to, let's say, the principal axes of the section, such that, I don't have that product of inertia term, or if I can reasonably assume that the section is symmetric, or it's, doesn't include that product of inertia term, then I can just kind of treat everything as an effective 2-dimensional problem. And then doing this inversion process is very straightforward. So a little bit of a nuance there, but, relatively straightforward and not really a complication for most problems. Now I can do the same thing given my curvature relationship. I can take its integral, get the rotation, enforce the boundary condition that at the left end, I'm also saying that the rotation of the section is constrained against, some kind of rigid motion or rigid rotation. So I can say that this function has to pass through 0 here at the left-hand side. And then lastly, I can take the final integral to relate section rotation to transverse deflection. And the actual diagram that I get is visually representative of the deflected shape of the beam. So it turns out that this ends up being a 4th order polynomial. If I started out with some polynomial of order n, let's say, then the deflected shape is going to be some polynomial of order n plus 4, because I have to take 4 integrals. It's a little bit of work, but once you get it, you basically know the deflection everywhere through here, and all these other functions along the way. So you can take, at any cut section, what's the internal moment at this section, or things like that. And it also makes visualizing and figuring out where is the maximum shear force, max moment, max rotation, tip deflection, all those things, a relatively straightforward thing to determine. Now, this is very nice. Obviously, you can go about solving these beam bending problems analytically, and in a rather straightforward way. It's just a matter of taking the integral 4 times, setting some constants of integration by applying your boundary conditions, and life is good. This is probably why so much time is spent in undergraduate coursework focusing on solving these beam bending problems, because they have nice, satisfying analytical solutions that you can determine. But what about plates? What about plates? Can we get analytical solutions for plates? Well, of course we can, but it's sometimes very difficult to get them. So first off, it's worth mentioning that in the case of plates, we also have slightly different boundary conditions than we would have in the case of a beam, and also different from what we would have if we had just kind of like a 3-dimensional solid. In this case, we have to specify boundary conditions along the edges of the plate. So rather than considering this kind of like pressure load on the surface of the plate as a boundary condition, it really is treated more like a body force than anything else. And really, it's only on the edges of this plate where we have to be specific about, are we constraining transverse deflection? Are we constraining rotation of individual fibers? And these fibers could rotate this way, they could rotate that way. Or are we specifying things like, are we saying what the transverse load is per unit width along this edge? Or maybe we're saying what the distributed moment per unit of width is along some other edge. And how you actually determine which components of transverse load, or which components of these exposed stress resultants on these different surfaces need to be constrained it gets a little bit complicated, but you can relate them to the different components through some kind of application of the Cauchy stress theorem reduced to the case of this, squashed down plate. So you can use Cauchy stress theorem to come up with this relationship between edge normal that has to lie somewhere in the plane of the plate. You can relate this edge normal multiplied by kind of the vector of all these different components of the, stress resultant quantities. Those are the MXX, MYY, and MXY quantities. And you can only specify two of them, really. You can either specify kind of like a moment like this that would lead to bending, or you can actually specify almost like a twisting, bending, torsional moment on these surfaces, kind of interestingly. In the case of transverse shear, there's really maybe only one quantity that you can specify, though. It's, obviously, whatever the transverse shear is, vertically, if that's kind of like your positive sign convention for shear. However, again, as I said, coming up with analytical solutions to these, plate bending problems in general requires solving that biharmonic equation, which doesn't always admit analytical solutions, at least not easily and not for general boundary conditions and loading conditions. But it can be done for certain types of problems, and the solutions you get look kind of like the ones that we did for these two-dimensional elasticity problems. They're kind of like you can visualize them in this two-dimensional sense, maybe as a contour plot to visualize what the deflected shape looks like. But again, in profile, if you were to look edge on at maybe the beam or the plate deflecting under whatever these transverse loads are, it wouldn't look so different in some ways to just, the bending of a beam. So at the end of the day, beams and plates, not so different. It just means that you have much more complicated solutions. And usually you don't go about solving these plate bending problems by applying, classical analytical solution procedures. Usually you would use some kind of analysis tool, finite element method to discretize the plate now into corresponding, plate or shell elements to represent how they would deform under the load. So at the end of the day, plates are kind of this weird middle ground. They're not quite beams in the sense that you can't really get good or easy analytical solutions to them as you would for beams. And they're not quite solids, but they still require usually applying some kind of computational tools to solve general problems when these kinds of things show up. So a little challenging, a little tricky. And it's made more complicated by the fact that really beams and plates, don't just undergo transverse loads, right? They also undergo in-plane loads or axial loads, depending on which of these two things you're looking at. In the case of beams, certainly you could have transverse deflection due to transverse loading, but you could also have axial deformation due to, axial loads that you would apply. And in general, those two things can happen at the same time. If you have a perfectly straight beam, then it's actually possible to decouple these two things and then actually come up with solutions that are basically superpositions of these two things happening simultaneously. So you can solve a problem that involves axial deformations independently of the transverse deflections, and then you can combine the resulting solutions together to represent what's happening to this whole beam under combined truss-like action or axial extension and beam bending. And the same is actually true for plates, where the analog to a truss-like member, in the case of a beam, which undergoes only axial deformations and axial stresses, the analog in the case of a plate is something called a membrane. A membrane is something that only, or at least ideally, only carries in-plane loads. It's kind of like the stress state in this membrane occurs such that there's no bending stresses that develop through the thickness of the plate. So you can think of classical types of membranes are usually very thin fabric-like kind of stretchy media, like a membrane or the surface of a bubble or maybe like a tarp or some kind of like tent covering and things like that, that have basically no bending stiffness. And they deform only under these kind of in-plane stretching deformations, resulting in these in-plane states of plane stress. So a membrane is basically kind of like you could think of it as equivalent to this two-dimensional thin plate type problem. So all the problems we solved in plane stress for these relatively thin plates were effectively membranes. They only experience these in-plane stresses undergoing in-plane deformations. But we can combine some of those solutions and superimpose them with plate deformations due to transverse loading and transverse deflection, and we can come up with more interesting behaviors that include both of those things, membrane action and plate bending action. Now, that's very nice up until you consider a few slightly more complicated phenomena. And in particular, I'll point to the case of curved beams and curved plates. Unfortunately, I won't have time to really dive into this subject. It's really nice, but unfortunately, when you have this curved beam or a curved plate, this idea that you could somehow decouple the truss-like action or beam-like kind of bending behavior of these things into two subproblems that you can solve independently, now that goes all out the window. Once you have a curved or initially curved geometry for a beam or a plate, there is inherent coupling between the in-plane or axial deformations that occur and the resulting bending kind of stresses that might result from that. And the simplest example that I can give to illustrate that is, just to consider a very simple, let's say, circular arc. It's like maybe a relatively thin beam that has some initial curvature built into it. And if you think about what would happen if you were to pinch the ends of this curved beam and try to just, pull it axially, basically stretch it such that, if this thing were initially straight, it would just yield perfect, axial deformation and axial stress through this kind of linear segment. But if it was initially curved and you're trying to pull it apart, now what'll happen, as you might imagine, if it was initially curved, it'll try to move more and more towards a straighter and straighter configuration. So as I continue to try to stretch it out, it goes from initially curved to eventually more straight. And to do that, it actually has to bend basically into this straight configuration. So in spite of the fact that I'm only trying to apply strictly, axial loads, at least along kind of this secant center line, if you will, of this member, it effectively develops these bending deformations. So conversely, also, if you had a kind of curved beam and you applied bending moments at the ends in an attempt to basically just incur only bending deformations, it wouldn't just do that. It would also possibly incur some kind of axial deformations. So there's inherent coupling that happens between axial or in-plane deformations for plates and resulting bending deformations and bending moments that develop. So that's the challenge with these curved beams and shells. And it gets more complicated when you have, maybe curvature that isn't constantly varying. You can do some simple analyses that look at, let's say, curved beams that have a constant curvature, like a circular arc, or maybe a cylindrical cutout of the surface of maybe a shell or a plate that's curved. But as soon as you have more complicated curvature that's varying and involves a lot of like minute kind of details, then at that point you need to invoke curvilinear coordinates and you need to come up with basically a totally different description of bending than the kinematics that we've developed. And that gets way beyond the scope of this course. It's really worth mentioning that, they're interesting subjects, but oftentimes when you try to represent these things, like let's say in a finite element analysis code, you can only really do it approximately. Most of the time, the types of beams and shells that they include in their actual analysis frameworks don't actually include that initial curvature. So really to represent the geometry, you kind of have to approximate it in this piecewise linear segmented way. And sometimes that's fine, and sometimes that's not so fine. But it usually means that if you're really trying to capture that curvature, you have to kind of use either specialized curved element formulations that can represent that, or you need to, use a lot of these kind of smaller subsegments to try to capture that initial curvature. So just be a little bit careful of that. Let's see. The other thing I wanted to talk about was composites. So both composite beams and composite plates. And there are various examples where this comes up. Obviously, composite beams could be built up sections of maybe some multi-material section. Maybe you have, I don't know, a steel I-beam that's, like a girder that's connected to some kind of concrete deck, and it's kind of like bonded through some shear studs or something. And the composite section of this whole, let's say it's maybe the section of like a bridge with these kind of steel girders sitting under this kind of concrete deck. To really analyze that situation, what you'll find is that, again, as I alluded to in kind of the previous lecture, it's no longer appropriate to assume that the stress variation through the full depth of this composite section that has a concrete deck and steel eye girders kind of underneath it, it's no longer appropriate to assume a linear variation of stress through the whole thing. And that has to do with the fact that right as you transition from that concrete deck and you go down into the steel kind of girders, there's basically a discontinuity in the representation of what the resulting bending stress distribution would look like. So it'll look kind of linear through the depth of the concrete deck until you get to the steel, and then all of a sudden it'll jump to something else. That's true also if you have, let's say, steel reinforcement inside of concrete. The apparent stress carried by the steel reinforcement is going to be different from the surrounding concrete. But in general, you still assume the same kinds of kinematics, more or less. You still assume that even if the stress distribution can't be assumed to vary linearly, you still assume that the plane section, which might include all these different composite materials kind of put together, you still assume that that plane section remains planar. And that's a reasonable assumption so long as the section isn't terribly deep. So if you have a relatively thin section, then that assumption of strictly planar sections remains valid. Where it breaks down, however, is as you have moderately thick beams or moderately thick plates, now that assumption of strictly planar sections, especially in the case of composites, is really not valid at all. And it gets really, really bad if you have, let's say, a many-layered composite material. You could think of that as like a laminated kind of wood structure, or in the case of this laminated sandwich panel. Getting me hungry. It's lunchtime after all. But this laminated sandwich panel has things like maybe aluminum, kind of skinned surfaces, and then maybe it has like this honeycomb core. I'm getting really hungry now. But this honeycomb core is really a lot less stiff than these kind of exterior aluminum panels. Sometimes they fill it with something else, like foam or something that's really not stiff at all, which basically means that the transition in kind of like that stiffness means that you could actually have like vastly different strain distributions that kind of kink, that they're not perfectly straight. They might look something like this. So if I had, let's say, this sandwich panel, let's say, and I wanted to know what's the actual section deformation. If I assumed it was strictly linear, or that this plane section remains planar, then it would kind of look like this, but maybe it would actually look something more like this. Let's suppose that this inner core material is relatively soft, such that it allows it, a lot of relative kind of like shearing deformations to occur. In which case you might see that most of the, if we're visualizing things like the axial displacement of this section under some kind of whole section rotation, within this kind of inner, core, it might look like this, but then here it might kind of taper off. So ultimately, you might have this assumption of planar sections remaining planar really being not valid if you have these, relatively distinct distributions between stiff material and soft material and like a layered composite. So just be aware of that a lot of the fundamental assumptions of beam theory and the kinematics inherent to that are really limited to certain types of beams and certain types of materials. So it's not just, the issue of, oh, is it thin enough? This can still show up if you have just even a moderately thick kind of plate or beam. So some issues there. And then the last caveat that I'll throw out there is large deflections. So even if you did all the other things to try to account for these different things, dealing with the issue of what happens if these plates or beams undergo relatively large transverse deflections, in those scenarios, you kind of have to invoke some different assumptions as to how you even construct the whole theory. Because the whole, Euler-Bernoulli beam theory and the whole of, Kirchhoff-Love plate theory really are centrally predicated on this assumption of small deformations. But if you introduce the possibility of large transverse deflections, large displacements, then it gets a lot more complicated, trust me. So we're not going to go there. I just want to point this out, that if you do have those situations, that, there are ways of doing that in an analysis setting, that a lot of finite element codes will allow you to actually do, different variations on how to deal with large deflections in these kind of like members that might be undergoing, deformations to a relatively large degree. And we'll talk a little bit more in detail about when that becomes necessary in maybe a week or two, when we close out on probably our last topic, which will be buckling and kind of the analysis of instabilities that might manifest in structures when the deflections potentially could be driven to relatively large quantities. And buckling instabilities are really driven by the inclusion of considerations for large deformations. So that's kind of a preview, just to get you a little bit excited about that topic. But we still have plenty of interesting things to discuss on the subject of torsion. Really a cool subject. It's a subject that doesn't seem terribly interesting from the outset, but I'll try to convince you that it really is pretty cool. So on the subject of torsion, we've talked about beam bending. We even alluded to the fact that for certain types of beam cross sections that are non-symmetric, depending on where you're actually applying the transverse loading, and depending on the type of section, you could inadvertently be cranking in some kind of internal moment. And it depends on, what's actually going on with respect to the shear stress distribution on a particular cross section. So if the cross section is non-symmetric, even if you're trying to apply transverse loading directly through the centroid of that cross section, that might still generate kind of like a torsional moment or a twisting kind of moment about the axis of that beam. And even if you didn't have that due to transverse loading, you could still have, let's say, relatively long shafts to which you're applying some kind of end torques. So twisting things. And that torsional moment torque is really characteristic of this phenomenon of torsion. So torsion really looking specifically at this case of just beams subjected to these end twisting moments and end twisting deformations can be analyzed again through the more general lens of the theory of elasticity. But before we dive into that, let me refresh your memory. Maybe you've kind of gone through this in, again, your strength of materials class or somewhere else. This hopefully will be a little bit of a review on the subject of torsion and how we idealize deformations under torsion. It's not so different in some ways from what we did for beams. Remember what we did for Euler-Bernoulli beam theory in particular. Actually, it didn't have to be Euler-Bernoulli beam theory. It could be, Timoshenko beam theory. Fundamentally, we assumed what? What was one of the fundamental assumptions of beam theory? Yes, plane sections remain planar after deformation. And that applied when we were looking at deformation of individual cross sections of a beam. We assumed that these cross sections could really only undergo rigid rotations. And in the setting of bending, we were looking at relative rotation of these cross sections about the transverse axes of the beam. But now, in the case of torsion, we're still going to invoke this same assumption, actually. We're still going to say that these plane sections, at least for the purposes of this initial analysis, and with a focus precisely on just axisymmetric cross sections like a circular bar, we can invoke this assumption and say that the planes sections of this kind of torsional shaft, this circular bar, are going to stay planar after deformation. So that is to say that if I were to cut through this cylinder, or maybe just consider the end cap of this cylinder, I can envision what happens to that end of this cylinder under torsional deformation by assuming that it undergoes a purely rigid rotation, but not a rotation about either of the transverse axes. In this case, it's a rotation about the actual axis of this shaft itself. So this section will undergo rigid rotation in its own plane, or if you like, rotation about the axis of the shaft. And in doing so, it'll undergo some characteristic angle of twist. I'll call this phi, if you like. You could call it something else. I think maybe the book calls it theta, but I wanted to distinguish phi, the angle of twist, from theta, which is kind of more of a cylindrical coordinate. So just to distinguish between those two things. Nonetheless, I can characterize what happens to the whole section and say that it undergoes, as a whole, this kind of rotation angle phi, the angle of twist. And in general, the angle of twist might vary along the entire length of this shaft. And if I looked at different points along maybe the edge of this shaft, I could mark maybe some initial line segment that was perfectly aligned with kind of the axis of the shaft, but just kind of like drawn on the exterior of this shaft. And if I twisted the end of this thing such that maybe it invoked some end angle of twist and a corresponding variation in the angle of twist all the way through the shaft, what I'll find is that initially straight line segment will start to kind of like twist along the exterior of the shaft. And if I looked at individual points, let's say, on this exterior edge of the shaft, I would find that they would undergo some kind of angular displacement. If you like, I could call this maybe the circumferential displacement, U sub theta, indicating that it's a displacement described within this cylindrical polar coordinate frame. So I have an axis X that's corresponding to the axis of the shaft, and then maybe I have my R and theta coordinate system defined relative to the center of twist of this shaft. So R measured from the center, and I can measure the distance of points relative to the center via coordinates R, and I can also measure what's the relative circumferential displacement, basically along the surface of this shaft due to these rigid rotations. And I can relate the angle of twist to the resulting circumferential displacement of any point at any arbitrary radial distance away from the center of twist through this relationship. And I can say that really it's the cross product of this rotation angle. Maybe if I wanted to represent it as a rotation vector, I could basically represent it as a vector whose positive sign convention by the right-hand rule would be basically, oriented in a direction as a vector parallel to the x-axis. Or I could just represent it as a single scalar number, because there's no ambiguity there. And I basically say that really the angular displacement is going to vary linearly as a function of radial position, such that at the center of twist, there's no angular displacement. And as I move further away, these kind of points will displace further and further along kind of like longer and longer arcs. So that's the basics of the kinematics of torsion. And it basically describes these kind of angular deformations in this cylindrical polar coordinate frame. And given this description of, you could call it circumferential displacement, we can then also apply our usual kinematic relationships or our strain displacement relationships. And if we assume in the case of torsion that individual plane sections undergo no other deformations apart from these kind of rigid rotations, then it's reasonable to just say that, well, the resulting strain that would develop, let's say shear strain under this torsional deformation, which we can measure by considering, let's say, some kind of, some kind of finite slice of this shaft. We can take out this, slice of the shaft of finite length delta x. We can look at, how does that little scratched line segment on the exterior after deformation, how does it look in this kind of side-on view of this slice? And we can notice that the angle or the relative inclination of this kind of diagonal line segment, that slope of this line segment is precisely basically the partial derivative or the slope of this angular displacement function with respect to axial coordinate. It so happens that through our usual strain displacement relationships, we can also come up with an expression for the x theta strain component, which so happens to be representative of the strain that would be experienced by, let's say, a small, initially square patch of material, but after torsional deformation might distort into this kind of parallelogram shape. And we can think of the resulting engineering shear strain, gamma x theta, which is just twice the tensorial epsilon x theta component, is really just the angle measured due to that kind of torsional deformation. So kind of nice. But again, it's important to emphasize that this only really applies when we have an assumption that these plane sections do indeed remain planar. We're going to upset that particular assumption a little bit later. But for the purpose of this analysis, let's just assume that they do indeed remain planar. Okay, now that we have shear strain. And if we assume that all the other components of strain, under our imposed kinematic assumptions are just zero, and the corresponding components of stress are also zero, the only shear strain and stress component that results is our kind of torsional shear strain, as shown in the previous slide, and the resulting torsional shear stress. And we can relate them directly to one another through just the shear modulus, G. The thing way back, in chapter, I think it was 2 or something, where we introduced this term. Now it's particularly convenient when you're dealing with torsion. Using the shear modulus is a nice way of just relating shear strains and shear stresses, particularly for kind of like these torsional shear stresses and strains. And once we have that, once we have maybe some variation in shear strain, we can relate it to a variation in shear stress, which varies on the cross-section. And as I said, it was interesting to note that there's kind of like a linearly increasing dependence of this kind of angular coordinate or angular displacement u theta as you get further and further away from the centroid of this cross-section. Right at the center, it basically means that also the shear strain and the resulting shear stress will also vary linearly as a function of radial position. So right at the center, you can kind of visualize how exactly do these variations in shear stress develop. They're zero at the beginning, and then they kind of grow radially as you get further and further outward. But they always have an orientation that is in the direction of basically the angular displacement. So it's always kind of shear stress that's pointed in kind of a circumferential direction. Now, knowing this, I can then come up with a way of representing not, a distribution of shear stress over the cross-section, but instead I can reduce it down into a very simplistic description as a stress resultant quantity, or as kind of a resultant torque, just by integrating contributions of maybe small moment arms R multiplied by the perpendicular, shear stress component to come up with a small contribution to the torsional moment that would be developed. And I can integrate over the full cross-section all of those different contributions of all these little small pieces of this cross-section at some distance R that varies over the section, and multiplied by some kind of torsional shear stress that varies also as a function of radial position. And if I integrate this thing over the whole cross-section, I'll come up with my representation of resultant torque. So I can represent everything in terms of that kind of big, long series of equations, or as I like to do in the case of beams, I can reduce everything down into a slightly simpler relationship that simply relates what I'll call this kind of rate of twist quantity, the partial derivative of the angle of twist as a function of axial position x. I can relate that quantity directly to the resultant torque that would act on this cross-section, involving our kinematic relationships governing how the shear strain should develop, including our constitutive behavior, and including our kind of definition of resultant torque on the cross-section. And in consolidating these different relationships, I come up with this complete, you could call it a resultant stress model. It's basically just a direct relationship between that rate of twist quantity and the resulting torque on the cross-section. And it involves dependence on two parameters. Collectively, these two parameters are sometimes called the torsional rigidity. But broken down, it really comprises just the shear modulus G and J, which is kind of the torsional constant. In the case of a circular shaft, or indeed in the case of any kind of axisymmetric cross-section, this torsion constant is really nothing more than the second polar moment of area, which makes things fairly straightforward to do and to carry out those integrals. You can also refer to tables to figure that out. Or if you already know what the Ixx and Iyy components are, you can also figure out what this J component is by basically summing those two quantities together. And it turns out to be the same thing. So second polar moment of area, different ways to compute it, but in the end, it really only applies in the case of axisymmetric shafts. That's where this kind of whole theory kind of ends. And again, we'll have to get into the details of exactly how do we deal with the case of non-axisymmetric shafts in a little bit. But I just wanted to complete the circuit and say that if you have, let's say, a bar undergoing some kind of end torques, you can pose equilibrium, basically moment equilibrium of a single bar, let's say, that might have, some differing torques applied to its ends, and maybe there's even some kind of distribution of torque applied along the length. So let's say a torque per unit length varying as a function of x, sort of like a distributed load, but now applied as a distributed torque. You can get creative in thinking exactly how would you apply such a load condition. But in any case, supposing you could, the actual statement of equilibrium of this whole bar is really just the sum of torques applied to this whole shaft. So maybe torque at the right-hand side minus torque at the left-hand side plus, the integral of this distributed torque along the length. And through a few extra manipulations, you could basically come up with a differential relationship that states how does the variation in this kind of torsional resultant quantity at different positions along the length of the shaft, how does that relate to this distributed torque that might be applied to this shaft? And it turns out, as was the case in beams, as was the case in a lot of different scenarios, you can do a bunch of fun calculus or other things and prove that, in fact, the derivative of this kind of torque, which varies along the length, is basically just equal to whatever this kind of possibly varying distributed torque would be, the torque per unit length. So kind of fun. And again, you can put it all into one big equation, as I like to do, and solve for just the single field of interest, in this case, the angle of twist. So you come up with, in this case, just a second order differential equation that relates the applied, distributed torque to the resulting rate of twist, I guess, in this case, or the angle of twist field, which varies as a function of axial coordinate along the length. Kind of fun stuff. You may have solved some of these problems by basically just assuming that the rate of twist quantity might have been constant. So just assume that this distributed torque isn't present and it's only subjected to end torques. That's a fairly simplistic problem that corresponds to this, what I'll call a Saint Venant problem. So Saint Venant, as you might recall from Saint Venant's principle, Saint Venant came up with this idea that if you have a relatively long, slender member, and maybe far away at the ends of this member, you're applying some kind of loading. It might be bending loading, it might be axial loading, it might be torsional, twisting loading, as we'll consider momentarily. But if this kind of member is relatively long, then you can kind of apply Saint Venant's principle to say that really, if I don't really care what's happening far away at the ends, wherever I'm applying these kind of end loads, then it suffices to just look at what's happening kind of at a section of this kind of long, slender member under the assumption that there might be some equilibrated stress field that arises due to, prescription of the net torque that acts over that section, but we're not going to be precise about exactly how that torque arises over the section. All we want to assume is that it kind of maintains a more or less kind of constant rate of twist over the length of this shaft. So each individual section is kind of like rotating a little bit and a little bit more, and we're not applying any kind of distributed torque along the length. It's just kind of rotating at a constant rate of change of that kind of angle of twist. So under these situations, it doesn't really matter what these boundary conditions are on the edges by Saint Venant's principle. We can just say it has to, whatever the torsional shear stress distribution is, it just has to be equal to maybe some net torque that we're prescribing. Now, let's take a look at a particular cross section in this torsional shaft, relaxing the condition that it has to be an axisymmetric cross section. And to make things simple, and because PowerPoint only really has nice ways of representing like cubic looking things, I'll just pick a square cross section. But it turns out square cross sections are kind of interesting. So let's look at this kind of square prismatic bar subjected to end torques. And looking at a particular cross section and remembering what was that fundamental assumption we invoked when we were looking at, this kinematic assumption of plane sections remain planar. In the case of axisymmetric cross sections, it was a valid assumption. In the case of even just like one of these planar sections, we're still going to invoke this assumption in order to figure out what exactly are the in-plane displacements that would happen to this cross-section under some kind of twisting deformation. So we'll still invoke this assumption, more or less, by supposing that maybe each section will undergo some kind of constant, angular displacement, such that the in-plane components of displacement in the y and z directions will be governed by precisely this kind of angle of twist for this particular cross-section. So we can still use that, but the thing that we're going to relax is this, the assumption of planarity. So in this particular representation, this illustration, and as was the case for circular shafts, we assumed that there was no kind of out-of-plane deformation or no axial deformation occurring on this cross-section. That's equivalent to saying that ux, the displacement in the axial direction, at all points on this kind of rotated cross-section is 0. So the plane section rigidly rotates, it remains planar, and that makes things relatively simple for the preceding analysis. We can basically just come up with what are the resulting shear strains that would develop, and they depend exclusively on these kind of components of uy and uz, the in-plane kind of rotated displacements. It assumes that these contributions that might come from the axial displacement don't contribute at all to the resulting shear strains that manifest under these torsional deformations. But what happens if I relax this condition? If I say that no longer do I assume that the section remains planar, instead I kind of introduce a general warping function. It's basically a representation of how the axial displacement might vary over the entire cross-section. It might not necessarily vary in a nice way. And at this point, we're making no specification as to how precisely it varies over the cross-section. For the time being, we can call this kind of axial displacement a warping function representative of warping deformations. And if you've never heard the term warping before, it's basically just characteristic or descriptive of surfaces that if they were originally flat, now they're kind of warped. They're not flat anymore. So in introducing this kind of warping deformation, this variable axial deformation over the cross-section, we actually introduce some new contributions to the resulting shear strains that would develop under the effects of torsion. Okay, and when that happens, it turns out that it doesn't really do too much, at least to our assumptions of how we come up with our resulting shear stresses. We can actually still figure out directly through the shear modulus how these kind of slightly more complicated representations of shear strain relate to these slightly more complicated representations of shear stress. And the complication here is that, previously I said, if you assume plane sections remain planar, it's valid to actually assume that this shear stress, the radial kind of represented in polar coordinates, will vary basically as a linear function of radial position relative to the center of this section. But that's no longer the case. Now it's possible that these different terms for the different components of shear strain and shear stress may not necessarily vary linearly relative to the center of the section. In general, they could be strange arbitrary functions of position that vary over the cross-section, and we would have to actually solve for them using our more general theory of elasticity. Now, how do we actually do that? Well, remember the other equations that we have to link everything together with. There's equilibrium. We've already gone through our kinematic descriptions, our stress-strain relationships. Now we have to apply equilibrium. If we happen to know that really the only components of stress that are non-zero are these kind of out-of-plane shear components of stress that arise due to torsion, all the other terms in our equilibrium equations go away. And let's also just say, for the sake of simplicity, that there are no external body forces, that the body force terms that would show up on the right-hand side of our equilibrium equations, that just goes away. Let's just say it's equal to 0. In that case, our equilibrium equations boil down to just these 3 expressions relating the different components of the shear stresses. We can also look at our expressions for the shear strain. And in particular, we can come up with effectively an expression of compatibility given these expressions for shear strain by taking partial derivatives of these components of shear strain with different components of either one of the two in-plane coordinates, y or z. And then we can kind of combine them in an interesting way. We can take maybe this expression and subtract from it this expression, and we'll get something that actually cancels out the dependence on this extra term that involves the warping displacement. So the warping displacement term goes away in this expression, and all we're left with is expressions involving these kind of in-plane displacements, and those depend exclusively on the angle of twist. Or more specifically, this kind of summed expression just gives us back exactly the rate of twist expression, or the partial derivative of the angle of twist function with respect to axial coordinate. We can also apply our constitutive equations relating shear strain and shear stress and plug them into this relationship to come up with the same expression, but just instead expressed in terms of the stress components, treating those as the primary unknowns that we will try to solve for in this kind of warping section analysis. And we come up with this final expression that is effectively a statement of compatibility, expressed in terms of these unknown and variable components of stress. All right, so now we have equilibrium, we have compatibility, and maybe you already kind of saw where this is going. But in analog to the way that we solved some of those plane stress problems way back in chapter 3, remember how we solved some of those problems analytically. We introduced something at that time which we called the Airy stress function. It was some, strange looking variable function of in-plane kind of coordinates and whose partial derivatives with respect to different combinations of the in-plane coordinates gave us descriptions of the stress components, which somehow magically, automatically, and always satisfied the equilibrium equations, such that we could just rule out having to consider enforcement of equilibrium altogether and just isolate attention to checking whether our presumed solution for this stress function happened to satisfy compatibility. It turns out that you can do precisely the same kind of thing in a slightly different variation on it. And, obviously people love to capitalize these things and put their names on it. So instead of considering these plane stress problems and analytical solutions by posing one of these strange, scalar functions whose derivatives yield the components of stress, in the case of torsion, the stress function is called something else. It's the Prandtl stress function. And instead of second partial derivatives of this stress function with respect to x and y giving the stress components, in the case of torsion, you only have to take a first partial derivative of this stress function to get the components of stress. The two components in this case of shear stress, sigma xy and sigma xz. Now, as I said, you can verify that, in fact, if you choose a stress function and you define the stress components in this way, you will automatically and always satisfy equilibrium, such that the only equation that you really have to check is compatibility. And if I've already expressed it in terms of my stress components, I can plug in, how those stress components depend on this Prandtl stress function, and I can come up with a governing differential equation that is a statement of compatibility expressed in terms of this unknown Prandtl stress function. And it turns out that this special function or this governing differential equation that results from it is actually just the Poisson equation. It's a particular differential equation of second order that kind of looks like this. Now, once you have this, and once you enforce a few extra conditions, in particular, boundary conditions, we can go about solving for what exactly is this warping displacement field by kind of first focusing on figuring out what is the distribution of shear stress that would result on the cross-section under these deformations, under these kind of general torsional deformations that might include warping. And to do that, again, we have to enforce some boundary conditions. And clearly, if we have some long prismatic section, and we're assuming we're not applying any external tractions on the boundary or the edges, exterior boundary of this prismatic bar, it's basically tantamount to saying that the exterior traction on these kind of outer edges has to be equal to 0. If you remember how we defined this traction vector, the exterior traction that acts on this exterior surface of this bar, we could determine what these components of traction are by using our Cauchy stress theorem to relate the individual components of the stress tensor to the resulting exposed components of shear or traction that would result on maybe this surface or this surface. And it depends which components will be exposed on the resulting surface normal. So if you're looking at this particular surface, you would have to determine what is the resulting surface normal, let's say n, pointed in this direction, that would determine through this expression what the resulting components of stress are that act on this surface. And if you know that the stress tensor really only includes these shear stresses, and if you're looking at these kind of surface normals that you know cannot have a normal component, if they are truly normal to this exterior surface, they can only have an orientation that is basically, which lies within this kind of in-plane YZ plane, then you can come up with basically a relationship that states some combination of these shear stress components multiplied by the components of this normal traction vector, or rather this kind of normal vector to this exterior surface, that in combination, in this interesting combination that depends on where you're looking on the boundary and how that normal is oriented, it imposes this constraint on those stress components, which is a little bit cumbersome to apply because obviously, if let's say the surface is a little bit curvy, it's not so clear how you actually apply this. But if you're looking at things from the perspective of solving not for the stress field directly, but instead solving for this Prandtl stress function, which is a scalar field, it's not a tensor anymore. You're not looking at components. It's just a single function of position that varies over the cross section. In general, if I substitute these expressions for the stress components with my expressions for the kind of like Prandtl stress function, assuming that the stress components come from the description of this single function through the different partial derivatives, I can come up with an equivalent application of this, free surface boundary condition by basically just saying that this Prandtl stress function, if I were to look at what it looks like and how it varies over the cross section, it might look something maybe like this. It might look a little bit different, but in general, what will happen in order to satisfy these kind of free surface boundary conditions, it turns out that I actually have to have this condition that on the boundary of the cross section, over this whole kind of like exterior boundary, I have to have that this function, the Prandtl stress function, is equal to some constant. It can't increase or decrease if I consider, what happens to the value of this Prandtl stress function evaluated along the exterior boundary of this section. And I can assign it to be any arbitrary constant I like. For simplicity, it's usually, done such that this, constant is just 0. So along the boundary, I say that this Prandtl stress function has to be constrained to be equal to 0. And if I do that, then I actually automatically satisfy this condition of a traction-free boundary condition on this kind of torsional shaft. So a slightly different application of how we would enforce these boundary conditions, now converting things into a slightly different format. But the last piece of the puzzle that we have to do is relate what is the resultant torque that might act on this cross-section. And again, we can do that by taking an integral over this cross-section, considering different components of this kind of exposed, these components of shear traction and how they would generate kind of small contributions to the overall torque or net torque over the section, expressed through a kind of an integral relationship. We can do a few mathematical manipulations and transformations in order to twist things around, and poof, we come up with actually an equivalent description of what the net torque should be on this cross-section, not in terms of these components of shear stress that might act and which vary over the cross-section. We can reduce everything down instead in terms of this integral that involves just a double integral, basically an area integral over the section of the Prandtl stress function itself. So it's kind of like if you think of the Prandtl stress function as being kind of like a bubble or something, the area underneath that bubble integrated over this cross section, or rather the volume underneath the bubble, is precisely equal to the torque, multiplied by a factor of 2. Kind of a crazy result. But ultimately what it means, and I'll end it here, ultimately what it means is that if you're going about trying to solve for these warping deformations, what they look like, I'll have to save the final result for next time to leave you in kind of a state of anticipation. But the idea is this: we obtain exactly those solutions for how the warping deformations occur, how the resulting shear deformations or shear stresses occur, and how they're distributed over the cross section. We do that by solving for this Fresnel stress function by enforcing the compatibility equation. It has to satisfy this equation, and it has to satisfy these boundary conditions that we've imposed. Both this condition that it has to satisfy the traction-free boundary condition on the exterior surface of the shaft, which is equivalent to saying the Fresnel stress function is equal to 0 along the boundary. And it also has to, in summation, net to something that looks like the net torque being equivalent to the overall integral of the Fresnel stress function integrated over the cross section. So we'll get to see exactly what these solutions look like next time, but just to give you a flavor, it'll be interesting. All right, so stay tuned. I'll see you next time.